Okay, this is day 3 of vectors. We're going to do a couple application problems. One of them is this first one's very similar to one we did yesterday. We've got two forces of different magnitudes and different angles acting respectively on an object. And we want to find the resultant vector. We're going to find the direction and the magnitude. So basically, yeah, well, I mean, we already did one like this yesterday. So when we look at this, give me just a coordinate plane real quick to start it. So we've got first force. Okay, I'll put that in red. 60 newtons and 40 degrees. So that first force, that vector is going to look something like this. Roughly 40-ish degrees, right? And I'll write it in there. And 60 newtons. Oh crap! No, I'm gonna just erase that. That looks terrible, but that's what you've got going on there. And then when you look at the other one, the second one is 70 newtons and 130 degrees respectively. And remember, guys, it's in respect with the positive x-axis. So it would be like your initial side would be here, and then you rotate around to wherever you need to be. So that 130 degrees is roughly here-ish. I'm going to make it just a little bit longer than the red one since it's 70 newtons instead of 60 newtons. And then remember, it's weird because when you're adding them, you take you start at the end of the first one, right? So I would start there. So really what I would do is I'd actually need to draw this. And here, my terrible dotted lines using this iPad and this pen. And so the resultant vector, wow, I'm a little bit too far. There we go. The resultant vector would be somewhere here-ish. That's not going to be great, but that's really what it would be. That's your F1 plus your F2, okay? All right, so just like we did yesterday, we're going to work through and find the component form of that first force vector. And so it is 60 newtons times the cosine of 40 degrees times I plus the sine of 40 degrees times j. And so when we get a decimal for that, we're going to get 45.96 I plus 38.57 j. And then when we do the second one, F2 is going to equal 70 newtons times the cosine of 130 times I plus the sine of 130 times j. And so when we get our decimal for that, we're going to have negative 45.00 I plus 53.62 j. And of course, the resultant vector F1 plus F2 is going to equal, remember, you're just going to take A plus A, B plus B. So when I get this, my F1 plus F2 is going to be 0.96 I plus 92.19 j. And so we want the magnitude of that, right? F1, F2. The magnitude, remember, is just the square root of A squared plus B squared. And so that would be 92.20 newtons. Okay. And then, of course, to find the tangent, oh, look at that. We'll go aqua. The tangent of the angle, the direction angle, is just B over A. So 92.19 over 0.96. Oops, 96. Thank you. And then, of course, plug that into your calculator, and your theta is going to be 89.40 degrees. So not too shabby on that drawing, because it would be really close to being a right angle. So yay me! All right, so we've got an audio speaker that weighs, sorry, I'm just changing my pen colors. An audio speaker that weighs 50 pounds, hangs from the ceiling of a restaurant from 2 cables as shown in the figure, 2 decimal places. What is the tension of the 2 cables? So this is, honest to goodness, basically what we just did. It's just a little bit more involved because instead of 2 force vectors, you've got 3. So what ends up happening is, and I'm going to draw this, I don't want to draw that in white because it's on white, so that's not going to work. Let me draw that in gray. maybe? Let's see if I can, no, yeah. We'll see if I can find a darker gray. Okay. All right, we'll do a dark gray. So I'm actually gonna put an axis on here, going through the point where it's actually being like held. So what ends up happening is you have three forces. You've got the force of this cable, you have your force of this cable, and then you also have, let me go with green, you have the force of the weight of the, the weight of the speaker. So here's the thing about this. It says it hangs from a ceiling. So when we see it like hangs from a ceiling, we assume that it doesn't move. Oops. Okay, so we assume that it's not going to move. So what that really means is these three, when added together, equal 0. It's in equilibrium, it's static, it's not moving. Okay? So what you're going to do is we're basically going to do exactly what we have done with the prior example and the last example from yesterday, but it's going to be a little bit different because what you're going to have is for this, and I'm going to name it force 1. So for force 1 here, you don't actually know the magnitude. So we're going to let the magnitude be A, but you do know the angle. And the angle is, remember, it goes from the positive axis, so it's going to be 135. Okay. Same thing for force B. You don't, or force 2, sorry. You don't know the magnitude, so we're going to let that magnitude be B. And then you do know the angle. It's just that 35 degrees, because right there it's just 35. Okay. And then for this one, we're going to name it force 3. You do actually know everything. You know the magnitude because it's the 50 pounds is pulling down. So that's going to be your magnitude. And then you do actually know your angle because remember, guys, straight down is 270 degrees. Okay. So what we have to do is we have to write those three forces in component form. So the AI plus BJ form so that you know what it is. So force 1 is going to be, I don't know the magnitude. So I'm just going to write A times the cosine of 135I plus the sine of 135J. All right. And so my A is going to have to, like, I'm going to distribute that A. So really it's going to be, it's going to look very, very weird. So negative 0.7, and you could use like X and Y, you can use W and Z, you can use whatever. I'm just letting those letters represent the magnitude. So negative 0.71 AI, okay, plus 0.71 AJ. So remember that A is a number. The I and the J are part of the vector component form. The I represents the horizontal component. The J represents the vertical component. But right now then, let's go to F2 and do the same thing. The magnitude, we just let it be B. And again, I chose A and B. You can choose X and Y. You can choose W and Z. You can choose, your first name initial and your last name initial, as long as they're separate, different. Just whatever 2 letters you need to represent that, okay? All right, I think I paused the recording, sorry. And then we're going to do B times the cosine of 35I plus the sine of 35J. Okay. And that's going to equal 0.82 BI plus 0.54 BJ. Okay, so, 0 there. Okay. And then F3 real quick. That one's going to be super simple because we actually have everything that we need for that. So the magnitude is 50 because we got the weight of 50 pulling down times the cosine of 270 degrees. You could do 270 degrees or negative 90 degrees. It's the same thing. I plus sine of 270 degrees J. So that component form is going to be 0I, right? Because cosine of 270 is 0. And then sine of 270 is a -1, so minus 50j. Okay? So now here's what happens. For F1 plus F2 plus F3 to equal 0, it means all of their I parts when added together equal 0, and all of their J parts when added together equal 0. All right? So I'm going to try to color code as much as I can. Let's make sure I got enough colors. All right, so I parts first. I'm going to take these 3 I parts and set them equal to 0. I'm going to make this a little bit smaller first before I go on. Okay, so those 3 I parts, I'm going to take them, set them equal to 0. So negative 0.71 AI plus 0.82 BI plus 0I, it doesn't matter, you don't have to put that in there, equals 0. All right, so really what I'm doing is I'm just going to add this to both sides and get 0.82 BI equal to 0.71A. Then I'm going to divide both sides by 0.82 so that B, oh, by the way, guys, I'm sorry, you don't have to put the I's in there. I'm sorry, you didn't need the I's. So just cross off those I's. Sorry about that. I wasn't thinking about it. You're really just taking the numbers in front of them. Get rid of that I there. So B equals 0.87A. All right, so then I'm going to take and get a different color, hopefully. We'll go orange. And I'm going to take the J parts. And again, just these 3 right there. Okay, so when I do the J parts, I've got 0.71A plus 0.54B minus 50 has to equal 0. But what I'm going to do is I'm going to take and plug this in here. So that way then I have one equation with one variable. So 0.71A plus 0.54 times, instead of the B, it's going to be 0.87A minus 50 equals 0. So obviously I would add 50 to both sides, so 0.71A plus this second term becomes 0.47A equals 50. And so then when I, 0.47, sorry. So then 1.18A equals 50. And so when I divide both sides by 1.18, I get A equals 42.38 pounds. Okay, and so that's actually the magnitude of that vector right there. And then to find the magnitude of the other vector, all you're going to do is, I'm going to have to shrink it a little bit. Sorry. To find the other magnitude, literally all you're going to have to do is use this right here. So B equals 0.87 times the 42.38 that you just found. And so that equals 36.87 pounds. And that's the magnitude of the force 2 vector. Okay? So again, a little bit longer, a little bit more involved, but honestly, it's just take it, like you've got 3 vectors that are, 3 forces that are acting on this. Write those forces in vector component form, and then just add up all your I parts, they have to equal 0. Add up all your B parts, they have to equal 0. It's just basically like a really ugly system of equations, and it's only really ugly because you have to use variables to represent your first 2 magnitudes, and then you got the I's and the J's in there as well that kind of throw you off, but it's really honestly just a system of equations.